Hi everyone, this is 1 p.m. sharp the Eastern Coast, and today we have Dr. Lucy Fortson, who is a professor of physics in the School of Physics and Astronomy at the University of Minnesota. As an observational astrophysicist, she uses very high energy gamma ray telescopes to study active galactic nuclei. She is also a founding member of the Zooniverse project, where over 2.5 million volunteers contribute to discovery research by performing simple data analysis tasks. Fortson focuses on developing human computation algorithm to tackle big data research. On the other challenges with next generation observatories such as LSST and the Cherenkov Telescope Array. Prior to joining the faculty at University of Minnesota, Forstall was vice president for research at the Adler Planetarium in Chicago and research scientist at the University of Chicago. She received her bachelor's degree in 1984 from Smith College in physics and astronomy, and her PhD in 1991 from UCLA in high energy physics. So please go ahead. You have your 45 minutes for presentation.
Okay, thank you. Before I get started, I do want to ask if others could potentially mute. There's a little bit of background. Yeah. Okay, thank you. Thanks very much, Gregory, and thank you so much for the invitation. I hope that people will get something out of this, even though I'm not a solar physicist. But we'll see. Eventually, there is a little bit of a link to solar physics. So in this talk, I will give a brief overview of the Zooniverse platform, in particular as a means to engage the public through crowdsourcing science efforts to help researchers tackle their big data problems. And that is, sorry, I have to get there we go. And so it's not, just my area of astronomy that is suffering from the data deluge. Of course, it's across all disciplines. The idea that we're being inundated with data from all of our different devices. And I actually, include pencil and paper here because quite a lot of our data is still in the form of pencil and paper. But so we have this data deluge, and for those of you who are familiar with this point, there's really just this analysis gap that has been growing between the amount of data coming in and our ability to analyze it, and that's due to what we think of as the 4 V's: the volume of the data, the variety of the data, the velocity of the data, and the veracity of the data. And I've added that last V for, our current era that we're living in. But in particular, a lot of work has been going into machine learning and how machine learning could potentially help close the analysis gap. And that does seem to work reasonably well for the volume of data and some level the velocity as well. But it's when we get into the area of variety and veracity that the machines still just aren't nearly as good as their human counterparts. And the other point is that machines are really only as good as what the humans tell them to do. And so they're only as good as their training. And those machines that have been developed that can help tackle the data deluge and close this analysis gap have been trained on images that have been identified by humans. So just to keep that in mind, closing the analysis gap by machines only is in some senses, not quite a false hope, but it's requires more behind the scenes work than maybe the folks that are pushing artificial intelligence might like to think. So I like to frame this as sort of a way that humans and machines can end up working together. And so what is it about the human that really brings to the table? What does the human bring to the table? And so I like to sort of ask this question this way, which is better at spotting the tiger, a computer with eyes, or a 5-year-old child? And of course, you know, we would all imagine, because evolutionarily speaking, the 5-year-old child has evolved to the point where if her ancestors had not been able to recognize the tiger, she would not be here. And so it's this pattern matching, this ability to detect anomalous events, or ask the simple question of what is this? What is this? That has allowed us to develop this amazing, complex image processing thing that sits between our ears. Okay, and so, you know, humans are definitely good at image analysis. The question is can we actually use humans other than just the few scientists that have been trained to do image analysis in a particular area? And so, you know, there's this question of cognitive surplus and the idea that, you know, humans do a lot of different things. Maybe they're not interested in helping to close this analysis gap. And so just to put it in perspective, it's 128 years every hour is spent playing online games. And so, you know, there's definitely a lot of cognitive surplus out there. And so we built the Zooniverse platform with this idea in mind that there are many humans out there who might like to participate in helping to close that analysis gap, given the proper tools and help. And so our hope was that this would sort of become the Candy Crush alternative for at least a few 100,000 or 1 million people. And so this started with the Galaxy Zoo project in 2007. I'll have more to say about that in a few minutes. About a couple 100,000 volunteers in 2007. And over the last decade, we've actually grown considerably to hosting 2.5 million volunteers who've made over 600,000 600 million classifications as of last night. And that's on a range of projects, not just in astronomy, but across the disciplines now. Over 300 projects have hosted a project on Zooniverse. And then, of course, most importantly, are the data that the volunteers providing. Is this analysis that they're doing actually helping to close the analysis gap? And sort of the coin of the realm there is their work actually being translated into peer-reviewed papers? And the answer happily is yes. And there are several hundred peer-reviewed papers that have come out of the work from the volunteers. And so on the right-hand side, it's just sort of the public-facing page that you get to if you go to the project page on zooniverse.org. You can select any project you want to filter by discipline or most popular or needs the most amount of work or what have you. You can go to the website and pick your project to work on. And another item that I wanted to draw to your attention on the bottom left is in the early days, we built custom web interfaces for different projects. That became the limiting factor. And so we built out a suite of tools in a do-it-yourself project builder. So any research team that is interested in putting up a Zooniverse project could quite easily do so through the project builder tools. And so you can see the growth really has accelerated with the launch of the project builder tools in July 2015. And so this is just, those that are, those projects that have been or are still on the website that are related to astrophysics or space science in some way. And so what are the kinds of tasks that we ask the volunteers to do? These are sort of the 4 basic tools. You can combine them in multiple different ways, but decision tree is the most basic one, a sequence of questions that can be asked and answers provided by the volunteers. Then there is marking, drawing tools that allow a volunteer to locate specific features within a given image. And then on the bottom left, we have a survey or filter tool that can be used in a wide range of projects, which are basically a fast way of getting classifications rather than walking through a laboriously long decision tree. If you have a fixed set of classes that you need associated or classifying an image for, then you can just do it in this sort of filter tool mode. And then the bottom right is transcription and annotation tools, where if you need actually some older catalogs, or in this case, the ADS wanted some captions annotated or transcribed and annotated to be better searchable. So those are the kinds of tasks that we have on the platform. And this is basically then the gist of how the Zooniverse works. The key point to take away is that we need multiple independent classifiers. And so this is effectively the central limit theorem, the idea that if you have multiple people looking at the same object or the same image and asked to do the same task, you can average across their votes. You can do more complicated aggregation techniques, but at the end of the day, you come to some consensus answer on any given image based on the task or the question that was being asked of the set of independent classifiers. And so there's a lot of devil in the details in terms of how to continue to present an image to a random person who happens to be on the system at any given time. And so, that's a lot of the infrastructure of the platform deals with that. But in the most simplest case, a project can just ask for what we call a brute force retirement, meaning you have to see, you have to show the image to 3 or more, up to 40 or even 80 classifications per image before the subject is taken out of the system. And so, as I mentioned, Galaxy Zoo was the very first project launched in 2007 with 1 million Sloan Digital Sky Survey galaxies that had to be classified. The key question, key science driver was to try to understand the galaxy evolution in the context of star formation and morphology. Blue galaxies tend to be spiral and are highly star forming. Red galaxies tend to be elliptical and dead. However, we're aware that there were red or elliptical galaxies that did have star formation related to them, but there weren't any algorithms. There were sort of crude algorithms that would give us the morphologies independent of the star formation. And so we wanted to get the morphologies without any other ancillary information potentially biasing the sample. And so the data were provided to the public in this fairly simple interface. Is it a spiral? Is it an elliptical? And it kind of went from there. It turned out to be amazingly popular, 150,000 users. In fact, I should mention, it was actually inspired by the NASA project Stardust at Home, which roughly about the same time, had about 20,000 volunteers working on classifying tracks in aerogel from the Stardust project. And so kind of inspired by that, we launched Galaxy Zoo, thinking that maybe we would get at best 20,000 volunteers. So we were very overwhelmed by the response, 150,000 users, which if you worked out the total number of classifications, 40 million on 1 million galaxies, it turns out to be roughly 3 1/3 continuous person years of effort, which is not something that you can really expect your graduate students to do if you thought that they might be able to provide you with the morphology catalog. So Galaxy Zoo, I mean, think about this. This is almost 15 years ago. Solved the so-called intermediate big data issue, where there were not enough experts at the time to produce the sort of morphological catalogs that we needed. So we're talking here scales of 1 million images. But what's going to happen when, as we're in the situation now, that we have much larger surveys coming online? And so, just for scale here, we can see the number of galaxies per day that are coming in from the different surveys, 2017, 2019. But when the Large Synoptic Survey Telescope comes online, really gets into its science phase, we should probably push this out to 2022 now. But the number of galaxies coming in is going to be the same order of magnitude per night that the Sloan accumulated in 10 years of data taking. And so that is just an impossible rate coming in. And even if we were able to harness the power of all the citizens on planet Earth, we would still probably not be able to classify the visual morphologies of all the galaxies from the LSST. And so clearly we need to deploy artificial intelligence at some level. So let's step back a little bit and go back to this point about training the machines. And so Galaxy Zoo not only solved the sort of intermediate big data challenge of having, 1 million galaxies that needed, more time than the experts had to give to be able to do the classifications, but Galaxy Zoo also then provided 1 million galaxies with labels that were able to be used for training machine algorithms for future labeling efforts. And so there, one of the more interesting results that came out of that work is there's a competition called the Kaggle competition, in which Galaxy Zoo was asked to contribute data and set up the challenge. And so we worked with 250,000 of our nearest galaxies. And the idea was to provide a subset of that for the competitors to train an algorithm. And we were hoping at the time that we would learn something more fundamental by whichever was the winning algorithm. We would learn something fundamental about the morphological structures. But in fact, the winning algorithm just took this idea that machines just need a lot of data to train well. And so Sándor Diliman, who is the winner of the competition, basically took all the images and did this data augmentation step, which is, this is back in 2015, when people were still really trying to figure out a lot of things about simple convolutional neural nets. And data augmentation was sort of one of those things that was just coming out. And so he just rotated the images, cropped them, and basically increased the number of images or the training set by a factor of 8. And so this just underscores the entire point that machines require large sets of images to train them correctly. And so again, from the Zooniverse platform perspective, it's not just astrophysical problems that are giving us this huge amount of data that we need to process. We have camera trap projects in ecology. So for example, this is the Snapshot Serengeti project that was launched in 2012. It had 7 million images that were taken over 6 seasons. This is a camera trap, 250 cameras set out in a grid in the Serengeti National Park in Africa. And the idea is that if you previously, to understand, for example, predator-prey relationships, you might want to take this beautiful lion and put a radio collar, which is incredibly invasive and is actually only then tracking that one lion. And so you don't really get the information that you really need. And so if you put up some camera traps that are motion or heat sensitive, then you can actually get the images that actually show interactions between predator and prey. The problem is, of course, is that you could have a lot of false triggers with even just a blade of grass blowing in the wind triggering the camera. And once again, we have the situation where we had a graduate student, Ali Swanson, who was tasked with the job of looking through 7 million images to find the few percent that actually had animal images and then even behavior indicative of behavior going on in those images. And so she turned to the Zooniverse to be able to help identify which images actually had animals and then to actually identify which species these animals were. So that was in 2012. And so the capacity, the importance in the ecology field of these results sort of basically hit us like a ton of bricks. And so we had many ecology projects, many camera trap projects then turned to Zooniverse to help solve their big data problems. And so both in astronomy and ecology and across all the disciplines, we're really in this situation where there's just too much data. And even if you're using citizen science techniques, there's still too much data, and you cannot possibly have each image looked at by multiple independent classifiers. And so you really need, again, to deploy artificial intelligence. But it's at this point that we ask the question, is it really true that all machines need is just large training sets? I mean, do we really just need to train the machines on images that have no animals in them and images that do have animals in them? What about more interesting information about species or interactions or things like that? And so this gets to this situation, which I sort of think of when I think about getting into a self-driving car. Not quite sure we're necessarily ready for this situation yet. I mean, the idea that the artificial intelligence has been trained well enough for a self-driving car to operate without fault is something that I would definitely call into question, as much as many companies would insist that it's okay to get into a self-driving car. So the other way to think about this is what we call in Zooniverse the Zorilla problem. And so I'm guessing, since most of you are solar physicists, or space scientists, you've never heard of a Zorilla. It is not a cross between a zebra or a gorilla. It is a small little skunk-like animal. Out of the millions of Snapshot Serengeti images, there were 7 Zorillas. And so this is where the machines have a problem. And this is why I don't trust self-driving cars right now, of course. It's this out of class modeling. So if you haven't given enough training data on specific types of images or specific classes, then your machine is going to fail. Again, the machine is only as good as its training. It's only as good as what the humans manage to label and give it. All right. And so, you know, taken to an extreme, can you have spoofing? Do you think, you know, can machines actually identify anomalies that are spoofed? And so, you know, this is again something where, again, with a self-driving car, you wouldn't necessarily want to trust that bad actors haven't tried to rig the system in some way. Okay. All right. So clearly, I'm setting the stage that machines are absolutely required for us to move forward into the next generation of data taking. But machines are not the sole answer. And so to, you know, this next part of the talk, I want to say a little bit more about what the volunteers do and why they're on our platform. And so right after Galaxy Zoo, when we had several 100,000 volunteers, we wanted to understand why they chose to participate instead of playing, for example, Candy Crush. Were they assigned by their teachers? Did they have some astronomy background and they just, you know, were attracted to that? Did they love, was it sort of the beautiful images, the beautiful images of galaxies that attracted them to the project? Or, you know, were they just really interested in the science? And so what was fascinating to us is that the most common motivation to participate in Galaxy Zoo was this idea that people wanted to contribute to research. And armed with that, that was what really gave us the intuition that a platform like Zooniverse would work. So another reason, which I sort of alluded to, why Zooniverse works is because you can get rid of the expert bias. And so if you just had a bunch of experts, even if they did have the time to go through millions of galaxy images, if you just had a few experts, they're often looking for very specific things, and they're trained to look, in some sense, very narrowly at a question. And so here we have examples of eye tracking software results where the reds are the sort of, you know, this is all sort of in a microsecond what the gaze of an individual is doing on a given image. And so, you know, if we were all together in a room, I would ask people to vote which one did they think was the volunteer or the non-expert and which one was the expert. But I'll just, you know, get to the punchline here. The bottom row is are the images that were classified by experts, and the top row is by non-experts. And so what you see here is you see the non-expert really doesn't know much about what this is, and they're looking for information in the entire field of view to see, you know, how they should respond to any given question that they've been asked about this particular image. And so, whereas the expert is, you can clearly see the expectation by the expert of tracing out the spiral arms here. Here, the expert is saying, well, maybe there's a little bit of a spiral arm here. I'm focusing in on that, but they pretty much, you know, get the answer pretty much right away. So why is that important? That is important because when you have these non-expert classifiers, they can ask questions of the data that an expert might not even think about asking because they're very narrowly focused in on something. Non-experts can see things, in effect, that experts have developed a blind spot for. And that is evidenced by what we actually saw happen on the Galaxy Zoo discussion board, in which people were encouraged to post examples of things that, well, they didn't know what it was. Strange things, the weird and the wonderful, as what we called it. And so you can barely see here, but in the, tiny center of this image posted by Hanne van Arkel is something she dubbed a green pea. And then that led to an entire set of volunteers who went out and collected green pea images. They labeled themselves as the Peas Corps. They had a lot of fun, but in some sense, more importantly, they were actually able, with the resources that we provided on the platform, to go find information and search for explanations about what these objects were. And it turns out that they had discovered, this is very high, saturated, if you will, O3 emission, which is a signature of very high star formation rates. And so what they had managed to find was an unknown type of galaxy, which they, of course, have labeled green peas, an entirely new class of galaxies that we believe are actually local analogs of what galaxies used to look like in the early stages of galaxy formation at the beginning of the universe. And so we can study green peas as these local analogs much easier to study and learn something about galaxy evolution. And this has led to, it's probably, by now closer to 400 papers on the topic of green peas. And what's fun about it is that the scientific literature refers to them as green peas. That's what they are. And that's because the people who discovered them were volunteers on the Galaxy Zoo project. And again, the key point is that Hanne van Arkel knew that the P was not at the center of the image. It was on, outside the main galaxies she was being asked to classify. But she had a sharp eye, and she noticed there was this odd object, and so she posted it. Likewise, she was a very active volunteer. By the way, she's a Dutch school teacher, elementary school teacher, teaching English to elementary school children in the Netherlands. And in her spare time, she wanted to contribute to research and loved galaxies, and this is where she found herself. She made another interesting discovery, which is now again known in the literature as Hanne's voorwerp. Voorwerp literally in Dutch means thingy or object. And so she thought it looked like, a space alien, but it turns out to be evidence for a quasar engine that's coming from the central part of the galaxy, having already ionized tidal features, tidal tails, through a merger interaction. And the ionized material is still emitting O3, but the quasar has turned off. And so this is something that had been predicted, but no one had ever seen this in action before, because of the decay time of the ionization is several tens of thousands of years, so fairly short in the grand scheme of things. So just to then really drive this point home, there have been many articles that have been published with Zooniverse projects where the citizen scientists have been co-authors, and certainly don't have time to get into many of them, but that is one of the critical takeaway points, is that humans have that ability to ask, what's this? And make serendipitous discoveries. And so this sort of flows into this idea that if you want to have a truly robust system that can tackle big data with a big B and a big D, you need to have both machines and humans on the system. So machines need citizen scientists as well. And so we combine them. Humans are able to make the serendipitous discoveries. Machines are able to take what they are trained to do and do it very quickly. And so we have set up a system whereby Zooniverse can tackle the big data problems through an optimal combination of both humans and machines to get through big data without missing serendipitous discoveries. And so I'm going to take the last 10 minutes and go through a few examples of the infrastructure that we've set up, and then close out with a little bit taste of history of what we've done with solar physics. And so I'm not going to spend too much time on the functionality, but just so you know that we have this ability now to integrate machine learning into the Zooniverse platform, where we can use it to help us retire subjects if a volunteer is in agreement with a machine prediction. We maybe only need 2 volunteers to agree with a machine before we can actually retire it very early. And so this can be then also deployed on a mobile app in which we can just effectively tenderize, just swipe left, swipe right, which do we think actually has a particular classification. That classification, again, could have a machine score associated with it. And combining all of that together, we found that we really needed we needed 43% fewer classifications. So this is really optimizing the efficiency of the entire system. We can do things like active learning. I don't have time to really get into this. If somebody's interested, we can talk about it in the question and answer period. But we can get to the point where we don't treat the machines as dumb assistants in some sense. There's a lot of work going on now. Going back to the self-driving car point, it really behooves the self-driving car companies to figure out what the anomalies are and to understand and categorize those anomalies, so we can use some of those same techniques to have the machine learn, well, when does it know the best thing, and what kinds of information does it need to best improve itself. And so it can selectively show the next best image to a volunteer to help it learn. So that is deployed on a couple of projects in the system. And then the flip side is sometimes we have very hard projects, and volunteers can I don't want to maybe get scared off a little bit because some of the tasks are very difficult. So we can train them and level them up through the difficulty, kind of training them, hand-holding them as the task gets more and more difficult. And this has been deployed on our gravitational wave detection project, Gravity Spy. And in that process, we also optimize the human version of serendipity detection. And in this case, the humans have detected new types of anomalous classes that can masquerade as gravitational waves. And so these are clearly things that need to be taken out and calibrated out of the detectors. Okay, so again, just a tiny little smattering of things that we've done on the Zooniverse platform that have incorporated machine learning to get this partnership going between humans and machines to be the most efficient at processing big data. So solar and space science on Zooniverse. In fact, it goes back to one of our very first projects beyond Galaxy Zoo, which is Solar Storm Watch. And it used stereo data and looking at coronal mass ejections, in particular from the you're going to laugh at me, but I think it's the Secchi imagers. And so there were 6 separate projects that came from these data, basically ranging from classifying when dust would hit one of the imagers, all the way to looking at video clips to outline what the storm front, the CME storm front, where it really was in the images. And so that ran for a couple of years and produced many papers, 7 papers. And I invite you to go read about them because there's some great results there. If you just go to this link down here and go to the Solar Stormwatch category. And inspired by that, they recently launched a further project in 2018, which wrapped up just last year, called Protect Our Planet from Solar Storms. And this is basically asking volunteers to classify the visual complexity of coronal mass ejections, and finding that the visual complexity traces the solar cycle.
Lucy, you have 5 more minutes.
Yeah, I'm about there. And then we just launched, literally a few weeks ago, a project called Solar Jet Hunters with SDO data. And this is a project led by Sophie Musset, Lindsay Gleesner, our host, Navdeep Bhansher, and several others. But I did want to highlight it because, in fact, this is how, Gregory and I met. And here the question is, in the first workflow, asking volunteers to identify if there's a solar jet at all in a 15-frame clip. It took literally 2 days for the 700 volunteers that were recruited to this site to classify 4,000 clips from the 2011 to 2013 data. 1,200 of those clips contained at least one solar jet. And then those are then passed to a second workflow in which the location of the jet base at the start point and the end point of the jet in time, and then, as you'll see, the length and the width of the jet at its maximum extent. And the goal of this project overall is to develop a machine learning algorithm to identify and locate solar jets. But here I want to then point out that this is the number of classifications per day for this project. You can see the project launch, that first workflow, it was very easy. The second workflow takes a lot longer to accomplish. It's a much harder workflow. But what's great is that we have this then highly engaged tail of volunteers that are continuing to contribute over 500 classifications per day on even a fairly difficult task. And so we're looking forward to being able to present results probably at next year's AGU on the results from this project. And so let me just finish up then by taking that last point about difficulty, task difficulty, and how we've shown through some studies, some sort of meta studies of the Zooniverse platform, that it's the engagement by the science teams on that leads to the best science outcomes. And so I don't have much time to go into this, but just to say that we know that science teams that do continuously work through blog posts, through talk board discussions, continue to engage, you're going to get people through those harder tasks. However, if you're also deploying machine learning on the system in what we did as an experiment, we thought that ethically, if the machines are now really able to remove most of what we call the blank images in our ecology projects, quite simply, then ethically we shouldn't be showing any of these to the volunteers. But what we found is that the volunteers would leave the system if they only got payoff images, if they only got animal images. So it leaves us with this interesting quandary. Do we spike these images with ones that we know the answer to already just to keep the volunteers on the platform? So these are interesting questions that we have to grapple with. And just to think that, remind ourselves that when tasks are hard or machines are in the loop, we need to be mindful that people are complicated. And so just remember that the main incentive for volunteers on the platform is they want to contribute to research. To do that, we need to keep them engaged through the harder tasks and to make sure that we message very clearly when machines are deployed, if at all, so that we're honest with them about that. And so I close with the summary slide. We're ready. If you have a project that you're interested in potentially mounting on the Zooniverse with whatever data set, please think about it. And I will then leave with an advertisement there. I forgot to put the due date on. It's June. I wish it were June. It's January 21st. So right around the corner, but there's still time. So if you really do have an interesting idea inspired by this talk, please do go check the seed funding program out and go ahead and submit a proposal. And with that, I thank you, our funders, and of course, all of our volunteers, without which this would not be possible at all.
Okay, thanks, Lucy. I think it's very interesting. So we are open for questions and comments. So please go ahead and mute yourself and ask question if you have any. So Lucy, Mark, yeah, go ahead.
So my question actually has to do with your last point where you said that if you didn't see basically that people just gave up if it was essentially too easy. So is this based on was there surveys done with people afterwards, or how does that determination get made?
Well, it turns out it's a fairly well-known cognitive science thing, and it basically it's a gambling. It's well known, unfortunately. Which is why it brings up ethical issues. It's unfortunately a well-known condition, if you will, for gamblers, and you know the casinos know what frequency that they have to provide a payoff to keep people engaged. Now, obviously, if you because you could have a payoff image, but then there wouldn't every time, but there wouldn't be a huge payoff, right? There would only be a small amount that came out. And so studying this and linking this to this kind of work, there are similar cognitive issues there. And so people basically get bored with seeing the payoff images one after the other. And so we found the optimum diet is between 5 and 8 unpaid, non-animal images for every animal image.
Yeah, this is Martin Lamming. There's something a little bit similar I'm aware of. During the Second World War, British coastal radar only detected incoming German aircraft during the first 30 minutes of a shift. And this happens now with baggage handlers at airports, checking for, the X-ray screeners looking at your suitcase. Again, 30 minutes is roughly all they can handle.
And it's this idea that our brain effectively becomes saturated.
Yes.
With the true positive examples.
And so the baggage handling thing, they sometimes they'll slip in a suitcase with what looks like an explosive in it to see if the baggage handlers catch it, just to try and keep them on their toes.
but that's right.
Doesn't
And
really work.
and then again, you get back to the ethical issues, right?
Yes, yes, yeah. This is just a human psychology problem.
Right. And so if we think of, we absolutely cannot think of our volunteers as machines, right? That would send everybody away. Yeah.
This is Jim Drake at Maryland. Can I ask one?
Please go ahead.
So I think you made a pretty compelling case, especially that in the future, the volume of data is going to be even much greater than we've had to handle in the past. And so I think you also made a convincing argument on a way forward, which I think is perhaps a combination of machine learning as well as people getting involved with that. So, but and the example of the jets was perhaps interesting because the people in our field can relate to that. But you were suggesting in the jet study that the people observations actually helped with developing a machine algorithm. And so I guess I'd like to know a little bit more about what it is about the human results from that project that actually helped you with developing a machine algorithm for that same thing. Because I have the impression from you that that's the future, and so I'm trying to see how the people observations could actually help with developing machine learning.
Yeah, and so just to be very clear, we haven't gotten to that step yet. So we've just launched the labeling part of that. And so once we do get the labels, and remember the labels come in two forms in this project. Is there a jet or not? And so even with that information, if you know that in a given video sequence, 15 frames video sequence, that if you just tell a machine, I'm going to pump in, a million 15 segment sequences, and I'm going to tell you that, which 20% of them actually have jets. The machine may learn, the hope is that the machine will learn then which segments in a future sample will have jets. And so you will have the machine telling you, instead of having the volunteers have to go through all of the data. Remember, this is 2011 to 2013. There's still quite a lot of data to get through. So the idea is hopefully that we can firstly develop an algorithm to identify jets, not just then on the SDO data, but any other potentially new type of solar data that might be useful for jet detection. And then the second step is this box, what we call box the jet. And so it's not just, is there a jet in this 15 segment clip, but where is it located, and what is its extent? What are its dimensions? And this is again something that once you have a starter set of labels from the volunteers, then you can pass that to a machine. And machines are actually quite good now at doing this sort of what we call region proposal exercise, where they, given the answer in the back of the book for a good fraction of the data, they can learn how to do their own boxing and region proposals. With, again, the point that once you have it trained on something like this, you can unleash the machines on a much larger data sample, which would take a very long time for the volunteers to get through.
Right, but I still don't see what it is about I mean, is it just a cross correlation between the decisions made by people and the decision made by machines, and you use, when you get a good correlation, then you conclude you have a good machine algorithm?
Just fundamentally, machines don't learn without labels. So you gotta start them with something. And the only way to start them is with human generated labels. Now, somebody who knows a thing or two about machine learning out there will take exception to that. But in general, you gotta start the machine algorithm with labels. So it isn't necessarily a correlation, so to speak. It's you rely on the humans to provide those initial label sets. Now, you can check to make sure once you have a machine trained that it's not drifting off course by getting volunteers, or by actually having them validate the machine answers, some fraction of them. I hope I'm understanding your question. And
Yeah, I think the thing you just said seems to make sense to me.
okay, all right.
Yeah, thanks.
Hello,
Can you
hello,
do-
Lucy.
Yeah, go
Hello.
ahead.
Yeah, this is Hossein Safari from University of Zanjan. Thank you for your very interesting presentation. My question about the performance of your machine learning method to identify or classify the different spiral galaxies. How you can measure the performance of the classification? What scores you have calculated for this machine?
Well, I mean, actually, we have quite a number of machines now on
Yeah.
but some of the earlier ones. Again, it's comparison. I mean, do you want the actual metric that we use, or do you just want the general?
Yeah. I mean, for the metrics, how metrics you used for the several type of the galaxies in your machine? Yeah, how you can measure the performance of the machine for classification of different types of galaxies?
Yeah, I mean, there again, we hold out. We have a gold standard set that we then use for training, and then we hold out some for the benchmarking of the data, and then it's just the usual sort of accuracy, like the ROC curves and that sort of thing, right? So, yeah, it's. I mean, you can look at the Dillerman paper. If you go on that publication site, there's a large number of papers that describe
Yeah.
the wide range of ways that we tackle that.
Yeah,
So,
yeah, that's great. Yeah, that's great. Thank you. My another question about the identification and tracking of the small features in the solar images, as you show in this slide, STO data. It's observe the sun at extreme ultraviolet or X-ray in corona. There is a lot of teeny features such as coronal bright points, blinkers, and etc. Is it possible to develop this machine to identify and track such very teeny features or not?
yeah, I'm afraid you were breaking up a little bit there, but I think this is what I've understood. You're asking, there are other features within the same data set. And is it possible to train an algorithm to identify those other features? Is that generally the question?
Yeah. My question about the application of this machine learning to SDO data, solar dynamic data, AIA at extreme ultraviolet. you see some very tiny features, small flaring features in the solar corona. Is it possible to apply such a method to identify and track the very tiny features on the solar corona or not?
Yeah, again, I'm sorry, Hossein. For some reason, I'm not hearing very well the specifics of your question. I'm sorry. It's probably because I'm also not a solar scientist. So I'm going to have to say, if in my understanding of the question, looking for other features in the data, yes, it may be that we could learn from the model that we generate with this, but it would depend on how different the features were that were of particular interest to you. And again, I apologize, I couldn't quite.
Yeah, thank you so much. It is maybe depend on the weak of our internet connection, maybe.
Yeah.
Poor internet connection, maybe. Yeah, thank you.
You're welcome to send me an email and
Attention.
ask it via email, and then I can try to better answer.
Yeah, of course. Yeah, of course. We are also working. I'm so sorry. Please let me to introduce in one sentence our works. We are also working on machine learning using the support vector machine classifier and some image processing on solar data. I will send you some of our papers to you, which was published in Astrophysical Journal and etc. Thank you so much.
Yep, great.
Okay, good. Let me ask a really quick question. So you mentioned at some point that some of citizen scientists are getting involved in publication as a co-source, as I understood. What are basically the criteria whom you would include?
That is dependent on the research team. So that is not something. So Zooniverse as a platform only requires that the data eventually become public, like they're accessible. The data meaning the citizen science processed data. We encourage the projects to continue to keep their volunteers in the loop as papers are being developed, as the analysis is being worked on. Yeah, so there are projects which do that very well. And for example, Mark Kuchner's group, Disk Detective, he actually has office hours, and probably 10 to 20 volunteers sort of on a bi-weekly basis work with him, in a sense, as undergraduates might work with him. And so he's very hands-on with his volunteers. Some are not as much that way, and are really, it's that first stage of discovery, the serendipitous discovery. They are involved in the sense that they're kept in the loop as the paper progresses. They're shown drafts. They're asked if they want to be authors, because they were the ones who made the discovery, but they're not actually deeply involved in any further analysis work. So there's a spectrum there of engagement, and a lot of it depends on the capacity of the research team to work with the volunteers.
Okay, great. Thank you very much. So we're on the second hour, so probably we have to conclude the meeting unless there is any more question.
I have a little time. If anybody else does, I'm happy to stay for another few minutes, but I understand that other people have to go.
Ivan?
Yeah. Hello, may I ask a small question?
Yes, go ahead.
Is like that. Did you encounter some bad persons who would like to foolish your system? And how can
Yes.
you deal with them? How you can fight with them?
Yes, that's a good question. Yes, even from the beginning, there were, bad actors. Typically, I mean, so you have to think, well, how are they going to spoof how are they going to, inject something into the system that means it's untrustworthy. And typically that means they are creating a set of responses to a given task that are either random or, you know, the nice thing is two things we can do. Firstly, they would have to harness like a huge number and then provide a large number of these attacks, if you will, because then that would, because I guess what I'm trying to say is it's the multiple independent classifier piece of this, which eradicates a lot of people who are trying to, you know, mess up the system. So that's point one. It's the system itself is robust against attack from that perspective because it's multiple independent classifiers. But also there are techniques that we can deploy in looking, we can monitor IPs, we can monitor the quote unquote skill level of a quote volunteer. And if somebody is clearly random, maybe it's not even that they're a bad actor, it's just maybe they're not that good. Or maybe it's a 3-year-old child who got the laptop or what have you. But these kinds of things can get filtered out. We can, if, for example, a lot of times attacks come where they haven't been very careful and they're very, you know, they dump a lot of classifications quickly. So you can actually look at the time of submission, the time difference of submission, and compare that to the standard submission frequency average. And then if people are off the charts, then you know it's probably a bad actor, and so you can take that out. So we have various techniques.
So did you already find a lot
yeah.
of this kind of
Oh, yeah.
cases?
Oh yeah.
Yeah?
Yeah.
Ah.
It's not even 1% of the classifications.
Okay, thank you. I wish you to have as less as possible this kind of cases to your system.
Okay, great. So probably let me thank Lucy again for very interesting talk and then discussion, which was again very, very interesting, I believe. Yeah. And that's it. So next talk will be in January, 3rd Friday of January. So please come back. Thank you. Bye.
Bye, and please don't